Today we'll revisit this problem, that is for every prime number except 2 and 5. We have some integer n such that p to the nth power is going to end with digits 0, 0, 0, 1. In the previous video, we use pigeonhole principle to prove this fact. For those who haven't seen the video, I suggest that you pause and go check it out. Now here we're going to use another method for the same problem, that is Euler's Theorem, which is a fundamental result in elementary number theory. So here we're saying that if we have integer n and a are co-prime, that is, they do not share common factors, then you have this relation here for the modulus n, a raised to this function called phi of n is equal to 1. Okay, so it's a generalization of Fermat's little theorem, and that's going to be the main result we're going to rely on for today's problem. All right, so what is the phi function here, or the Euler's Totient Function? It counts for a given integer n the number of integers that are relative prime to n. All right, so of course we count the number less than n. Right, so for example, integer n equal 10, you know that for the integer from 1 through 9, so we have 1, 3, 7, 9, that is relative prime. For 2, there's a common factor. For 4, of course, common factor. For 5, also a common factor. So here the phi function would be to count the number of such numbers. All right, so that's going to be 4. For an integer, how do we calculate this, right? Is there any formula for this? The answer is yes. We're not going to cover the detailed reason for this, but we're going to share these basic results with prime factorization and Euler's Totient Function. If we have the n, integer n, as a factor of a bunch of p with different powers, then with these we can calculate the totient function phi, which is n times this. Okay, this expression is very useful in calculation of the totient function. All right, now in our case, we're considering not 4 digits, so we need to consider the behavior with modulo 10,000. So it's interesting to know what is a 10,000 phi, right? So for 10,000, that's 10 raised to the 4th power, and prime factorization is going to be 2 to the 4 and 5 to the 4. So plug in the formula here, we're going to have 10,000 times 1 minus this, 1 minus that, and if you do the math, that's be 4,000. We need to prove this, and we're going to use Euler's theorem here. So this is Euler's theorem, and we have a and n. We need to choose what is a and what is n. N, of course, here is going to be 10,000. A would be our prime number p, and of course, n and a in our case are co-prime, right? P and 10,000, because p is not 2 or 5. For any other prime number, it's going to be relative prime with 10,000. And we know, of course, when we calculate phi earlier, we use the formula, that's 4,000. So plug in the theorem saying that p raised to the phi, which is 4,000, is going to congruent to 1 modulus 10,000. That is, for any prime, if you raise to 4,000, then the remainder has to be 1. That is, not 4 digits, it's going to be 0, 0, 0, 1. We prove it. Okay, so these are results. When n equals 4,000, and that's going to end with 1. All right, so we have shown that for the prime p, 4,000 power is going to be 1, right? The remainder. Now the last 4 digits is going to be 0, 0, 0, 1. Now the question is, are there a smaller number than n, such that that's equal to, the modulus equal to 1? In other words, smaller n, so that this is true, right? The digit ends with 0, 0, 0, 1. The answer is yes, right? So there is a fundamental results in abstract algebra regarding the order of an element in a group. We're not going to use that. We don't assume you know the results here, right? But we do some experiment. Let's write a Python program to find out the smallest n such that this is true, right? So how do we do that? Let's go. Let's switch to a Python program here. Right, so let's try to find smallest n such that p raised to the nth power equal to 1 mod 10,000. We're going to define a function, find smallest n, right? With, for example, prime p here. Let's do a dictionary. Keep track of the current remainders that we have seen. Okay, remainders, right, is a dictionary, right? So, and then we're gonna let n equal 10,000. We're gonna let the remainder initially be 1, and for the prime p, every time we're gonna type the remainder by p is gonna be the next power, right? So for I in range from 1, 4001, because so here the real remainder is going to be the previous remainder times p as we increase the power each time, right? In order to avoid like overflow, even though Python can handle huge numbers, but let's always keep track of the remainder only. You know, this is n here, right? And if we have seen that, if r is already in the remainders, what we're going to do is we're going to calculate the difference here, which is the current value I minus the previous value we have seen, the remainder, with key I, okay, key r. All right, so we're going to return the value here, else we're going to put this into the remainder, right? Remainders r equal I, and we're going to return 4,000 if somehow there's a bug or whatever, right? So let's run that. Let's try it, right? Let's to find smallest n with p equal to 3. Oh, 500. Okay, but how about some other p? We're gonna primes. We are interested in maybe 3. It's not 2 or 5, so it's gonna be 7, 11, 13, 19, 23, 29, for example. We're gonna do a for loop for p in primes. We're gonna print out p and the integer, smallest integer for p such that the remainder is 1, right? So let's run that. Another 500 and there's 100. That's the results. Okay, let's go back to the slides. So from the Python program, we know that all these numbers we have tried, and a bunch of them are 500, right? And for 7 is just 100, right? So notice that they're all factor of 4,000, right? But in general, so how do we prove that, right? Let's say if the smallest number n less than 4,000, if it exists, we're going to have a simple proof, right? So assume 4,000 can be expressed as a multiple of n with some remainder here, right? The remainder, of course, is smaller than n, right? So here we're going to say 4,000 equal this. Now we know that n satisfies this equation here, that is the remainder is 1, right? Mod 10,000. So what we have is that both 4,000 and n satisfies this property here, right? But what you can do is you can rewrite this as, because p to the n is modulus 1, right? So you can rewrite this part here as you can split into 2 parts, and this is 1 raised to the q power is 1. So what you do is p to the r is going to be equal to 1. All right, so which means n is the smallest integer such that the remainder is 1 with the power, right? And we know that PR is also this. But, you know, R by definition is going to be less than n or greater or equal to 0, right? So because this is how we can express 4,000 in terms of nq plus r. R is the remainder when divide 4,000 by n, right? So which means r can only be 0. In other words, 4,000 is going to be multiple of n. N is a factor of 4,000. That's a proof. All right. Anyway, so we cover a lot of stuff here. For those of you who are not familiar with Torsion function, go and check out some background materials on the internet. And hope you enjoy the video. Please like, share, and subscribe to the channel.